Hi everyone, today we'll begin a discussion on new chapter, Transformation of Stress and Strain. Before beginning today's lecture, let me give you a review of previous lecture. So in previous lecture, we discussed about three topics. First, longitudinal shear. Second, the shearing stress in symmetric thin-walled member. And as a third topic, we discussed about unsymmetric loading and shear center concepts. Okay, so let me give you a brief review of that. So I told you that even though we apply a vertical shear force V, we can have a longitudinal direction, like a orthogonal direction to shear force direction shearing stress. And the reason is, from the mechanical equilibrium analysis, right? So to satisfy mechanical equilibrium analysis, mechanical equilibrium, then we need some support force from these two sides, because at least for this case we don't have any force on top and bottom. So the only way to sustain the mechanical equilibrium out of this two normal stress from like a moment in left and moment in right, and if you have some sort of side force, then you can make a balance, and due to the tau xg and tau gx equivalence, you can have this kind of longitudinal shearing stress, or you should have this longitudinal shearing stress to satisfy mechanical equilibrium for this red area, right? So how can we obtain that? We can use the formula we developed. However, for this case, because we have two identical surface where we have the same q, so we instead of vq over I, we use vq over 2I, and in obtaining the q integral, we focus on this red area, and we can simplify the integral as the area of this red one multiplied by the position of this red guy, which is this is y bar red. Okay, and after plugging the characters we have, the L and T and H over 2, we can obtain Q integral in analytical form. And regarding the I for this hollow square cross section, then we can do these kind of computation, like the full cross section minus smaller cross section which has the same size with the hole. Then we can obtain the I relatively easily. So in this way we can obtain the longitudinal shear for some hollow structures. We then discussed about like a general thin-walled member. The characteristic of a thin-walled member is that because we have stress-free surface here, stress-free surface here, the only way to satisfy the equivalence between like a tau in one surface and tau in the other surface is that this shearing stress must be parallel to this thin walls. Okay, so this is the requirement for shearing stress in a thin walled member. The reason why we put symmetric is our equation only holds if there is no twist. Okay, because if we consider unsymmetric member, there can be possibly some twist. We make a emphasis on the term symmetric. And if we consider this symmetric thin-walled member where we can apply our derivation regarding Q, then we can obtain the entire shearing stress distribution using this formula. Okay, so the calculation of this Q integral, it will be depend on the specific situation. And another thing also I told you is that when you take this red area, please try to get red area where you have as much as possible this free surface without any stress, such that you only have Q here, or you can take a very symmetric red area, such that out of all this, you have the entire stress-free area except this surface, such that you can obtain the shearing stress at that position here. Okay, so if you follow this rule of thumb, yeah, you'll be you know you'll be able to find the shearing stress distribution really easily based on our expression for the Q. Then we discussed about unsymmetric loading and shear center. Even though, yeah, we we didn't discuss about the general unsymmetric loading, including the twist, because it's out of the scope of this course. We somehow consider this problem in different way. Only if there is no twist, we can apply Q equals to be VQ over I equation. And the approach we have taken was we assume that there is no twist, then we can draw shearing stress distribution based on this equation. Then after obtaining this shearing stress distribution, we can obtain the the force distribution at flange and web and flange area. Okay, and after looking at this, we can convert this to equivalent to a statically equivalent problem, including only one shearing force, such that summation of fx, summation of fy, and summation of torque are equal to each other between two problems. Then from this criterion, yeah, we can obtain the position of shear center. Okay, and then we say that if shearing force is applied at this position, like a distance e from the web area of the sky, then it will follow this shearing stress distribution, and the distribution will be something like this. Okay, so these are the logic we have used when discussing about unsymmetric loading. For general unsymmetric loading, including the twist, yeah, you gotta take advanced mechanics course. Okay, so with that, I can summarize the concepts we covered in previous lecture, and let me close the review at this point.